Okay, class, welcome to class 21 on Maxwell's equations. And we're finally coming to the culmination of our academic work. After this, you'll be doing some projects extending our study of electrodynamics. This covers section 7.3 and wraps up the material we've done so far into 4 very famous equations which encapsulate along with the Lorentz force equation, a lot of, or almost all of, classical electricity and magnetism. So the Maxwell equations. So let's look at electrodynamics before Maxwell. It turns out there's an inconsistency in the equations that we have so far, which we haven't looked at them all together, but we'll notice now. So let's just review those equations. The first equation is Gauss's law, the differential version, that the divergence of E is the charge density rho over epsilon naught. The second equation is that the divergence of B is 0. That says no name, although it can be thought of as the fact that there is no magnetic charge or magnetic monopoles. The third equation is the one we just introduced last class, called Faraday's law, which says that the curl of E is minus the partial of B with respect to T. That is, a changing magnetic flux can induce an EMF, or also known as an electrical circulation. And the fourth equation which we had, which is the differential version of Ampere's law, is that the curl of B is mu naught times J. Okay, so that a current causes a circulating magnetic field around it according to the right-hand rule. So Maxwell originally did, who worked in the 1850s and 1860s, a Scottish physicist, very brilliant mathematician, but also with physical insight, following up on the work of Faraday, who we looked at last time, thought about this circuit. And you can see this circuit has a battery and a capacitor, 2 plates here. And he thought about applying Ampere's law to this portion of the circuit right here where the arrow is, and this loop, Amperian loop here. Okay, so if we do the if we write the integral form of Ampere's law, it's the line integral of B is equal to mu naught times the current enclosed. So if we make our line integral around this surface here, then the current breaking through that surface is just the current in the wire, and so we do get a circulating magnetic field. However, there's nothing which says that in the mathematics which says that the surface which is bound by the Amperian loop has to be the interior of the surface. So Maxwell imagined that the surface could be this sort of bubble which extends back across into the field, into the gap between the capacitor, of the plates of the capacitor. And then if we do that, then if you think about it, the current can only flow in the wire. The current can only flow in the wire, and so there's no current flowing between the 2 capacitor plates, and so there's no current flowing anywhere through this sort of soap bubble-like surface. And yet there is a circulating magnetic field around here. So he saw that as a contradiction to Ampere's law and wanted to fix that. So that's kind of was his physical intuition. So there were 2 possible surfaces to use to find the current. I enclosed the interior, which worked, and then this other bubble-like surface which didn't have any current going through it, and so seemed to give a contradiction. Mathematically, if we take the divergence of the curl of E, that should be 0, because the divergence of the curl of a vector field is always 0. And we know that the curl of, from Faraday's law now, we know that the curl of E is minus dB dt. So we have the curl of minus dB dt. We can interchange the space and the time derivatives, and we get minus the time derivative of the divergence of B. But the divergence of B is 0. And so we get this is equal to 0, and so we do have divergence of curl is equal to 0. So that is consistent. But if we try the same thing with, instead of with Faraday's law, with Ampere's law, we get the divergence of the divergence of the curl of B, which should again be 0 mathematically, is equal to mu naught times the divergence of J. But if you look way back in your notes, the divergence of J is basically how much charge is flowing out of a given volume, and that's related to how the charge density is changing at that point. And it turns out to be, this is called the continuity equation. It basically says that charge leaves a given volume only if it flows out through an area enclosing that volume. So this term is not 0 because charge can change at a point. And so physically, we have an equation on the right-hand side which is not 0, but mathematically on the left-hand side, it should be 0. So that's the inconsistency. So we have the physical inconsistency and also the mathematical inconsistency. And so, okay, so Maxwell thought about this and thought that he needed to fix Ampere's line integral law to make the whole set of equations consistent. So taking Ampere's law, the curl of B is equal to mu naught J, we have, as we said before, the divergence of the curl of B is mu naught del dot J, and the divergence of J is minus d rho dt. So if we could add a term to this equation such that we got, when we took the divergence of it, we got plus d rho dt, we would get 0 for the divergence of the curl, and we'd be mathematically consistent. So let's follow this along. According to the Gauss's law, rho is equal to, rho is equal to epsilon naught times the divergence of E. Okay, so if we come back here, rho would be equal to epsilon naught times the divergence of E. And then we can again interchange the space and time derivatives, and we get minus the divergence of epsilon naught dE dt. Okay, so the divergence of J is minus the divergence of epsilon naught dE dt. So that suggests that if we just add on to this side a term involving epsilon naught dE dt, then we can cancel this mu naught times the divergence of J and get 0 for this divergence of curl, as we should. And that's what Maxwell did. He suggested that the curl of B should be equal to, yes, as Ampere said, mu naught times J plus mu naught times this term here, epsilon naught dE dt. Because then if we take the divergence, we get mu naught times the divergence of J, but then we also get minus the divergence of mu naught epsilon naught dE dt, which is equal to mu naught minus mu naught the divergence of J. So we get a cancellation here, and the divergence of the curl of B in this equation, these two divergences cancel through Gauss's law. So we can write this in integral form as the line integral of B is equal to mu naught I plus mu naught epsilon naught times the surface integral of dE dt dot dA. Or if you like, we can bring this d dt out in front and we have just the time derivative of the electric flux. So we can say that a changing electric field, or if we like, a changing electric field induces a magnetic field, or a changing electric flux, if we bring the divergence out here, induces a magnetic circulation. So we have kind of a full symmetry here. We know from Faraday's law that a changing magnetic flux produces an electrical circulation. Now we have a changing electric flux producing a magnetic circulation. So we get a greater symmetry between the electric and magnetic fields. And then let's go back to this problem, the physical problem, which Maxwell talked about, which was this circuit with a current flowing through and one loop which had current, one surface of a loop which had current flowing through it, and another surface, this bubble surface, which didn't, and see how this new these new equations can resolve that. So resolving the physical puzzle of the circuit with the capacitor, again, a changing electric field induces a magnetic field. So we have our new Ampere's line integral law, often called the Ampere-Maxwell law. Maxwell called this term epsilon naught dE dt the displacement current, and it's equal to just epsilon naught times dE dt. So it's whatever is multiplying mu naught times the physical current plus mu naught times the effective displacement current, which comes about from the rate of change of the electric field. So if we look at this physical situation, what's really going on here is that as current flows onto these plates, because current is flowing onto this plate, charge will build up here on the left plate and charge will leave the right plate. And so the electric field, with more and more charge here and less charge here, the electric field will gradually strengthen in between. And so there's a change in the electric field with respect to time. And so we get a displacement current or a change in the electric flux in between the plates. And that's enough to cause to give us this circulation of magnetic field around, because the displacement current can act just like a real current in producing curl of B or circulation of B around this loop. So let's just look at this computationally. From Physics 202, when we have two square capacitor plates, if they're big enough and close enough, it turns out that the electric field between them is equal to their charge density, that is the charge per unit area, over epsilon naught. That follows from Gauss's law. And so the charge density is the total charge Q on each plate. So it'd be like plus Q on this plate and minus Q on this plate as charge flows off of it over the area of the plates. And so the partial of E with respect to T is equal to 1 over epsilon naught A times dQ dt, because epsilon naught and A are constant, dQ dt. But what is dQ dt but I? The current, the rate of change of the charge on the plate, is just equal to the current. And so therefore, If we calculate the displacement current, it is epsilon naught times dE dt, which is 1 over epsilon naught AI. So the epsilon naughts cancel, and we just get I over A. So it would just be, the displacement current would just be the current that's flowing into here distributed over the area of the plate, which is exactly what we would imagine as the current density, the current per unit area. Okay, so so this leads us, solving that mathematical or theoretical problem, as well as that physical puzzle with the capacitor plates and that circuit, led Maxwell to his equations. And the first 3 equations are not changed. We just have the divergence of E is rho over epsilon naught, Gauss's law. Divergence of B is 0. The curl of E is minus dB dt, that's Faraday's law. But now we have Ampere's law with Maxwell's correction. And this tells us that even in the absence of a current, if the electric field is changing, we can get a magnetic field or a magnetic circulation produced. And together with the Lorentz force law, which, if you remember, is the force on a charge and the presence of an electric field and a magnetic field, we have F equals QE plus V cross B. These 5 equations constitute basically all of classical electrodynamics. Now there's a lot of more details to work out, as I'll say in a second, but we've reached a real summit and a real peak here, which the vector calculus has helped us to express in a very compact way. And just as an aside, now the continuity equation, which before we had to kind of argue for on physical grounds, that is that the charge flowing out of a given volume is equal to minus the amount of charge density leaving, or the rate of change of the charge density in that region, is actually implied by these equations, because if we look at the equation 4 and we take the divergence of it, the divergence of the left-hand side is 0 because div curl is 0. So this is 0. We can cancel the mu naughts. The divergence of J is what we have on the left-hand side here, and then this, the divergence of epsilon naught dE dt, can be shown to be equal to minus, d rho dt, according to Gauss's law. So the continuity equation is implied by Maxwell's equations. And then some offshoots from Maxwell's equations, which you might investigate in your projects at the end of the semester. We have Maxwell's equations in materials. When electric and magnetic fields are applied to materials, they polarize those materials and create magnetization in those materials. And we can incorporate those into Maxwell's equations, incorporating the polarization and the magnetization in a very nice way. A slightly altered set of Maxwell's equations that apply within materials. These equations are sufficient to figure out what happens at the boundaries between interfaces. So like when light, or when electric and magnetic fields, which are constitute light, as you probably already know, go from air to glass or from glass to water. These equations help us to figure out how the electric and magnetic fields have to change at the interface, what boundary conditions they show, and we can derive the law of reflection, the law of refraction, effects of polarization on the reflected and transmitted rays. And then finally, the solution kind of historically, the most amazing thing about Maxwell's equations was he came up with them without any experimental input other than the work from Faraday. And if we take out the charges, so if rho is equal to 0 and we take out the j, so j is equal to 0, these equations look very symmetric. The divergence of E is 0, divergence of B is 0, curl of E is minus dB dt, curl of B is plus this constant times dE dt. But you get a very symmetric set of equations. And it turns out that those equations support traveling wave solutions, which Maxwell showed. And he showed that those waves travel with a velocity equal to an expression involving this combination of constants, mu naught and epsilon naught. Specifically, it was 1, he found it was 1 over the square root of mu naught epsilon naught. And these constants were known from experimental measurements, and when he calculated this out, he found that it was within less than 1% of the speed of light known at that time. And so Maxwell hypothesized, or he concluded or hypothesized very strongly, that light must be made up of electric and magnetic fields sort of self-propagating each other. And later, he made predictions that there would be electric and magnetic fields of different types, different frequencies, and I don't know, 10 or 15 years later, Heinrich Hertz discovered radio waves, which had not been observed before, and they traveled at this same speed c in vacuum, or in air, which is essentially a vacuum. So this would be another. This would be other possible projects for the last couple weeks of the class. Okay, so here we've arrived at Maxwell's equations. I hope you, now with vector calculus under your belt, you can appreciate them. When you wear a t-shirt with them, you kind of can talk about, or at least know what they refer to and what physical effects they describe. All right, great. Thanks for your attention, and see you in class.